Here we have a Newton's third law kind of question. It does use Newton's second law because that's the only one with an equation, but it's kind of one of these action-reaction questions, which is Newton's third law. What we've got is we've got box A, it's a mass of 6 kilograms, box B, mass of 12 kilograms. They're tied together with a rope, and then we're pulling on box A, another rope, I guess, let's say, and we pull on block A with a force of 36 newtons. We're going to find a couple things. We're going to find the acceleration of the two boxes, and then we're going to find the tension in the rope that connects them. If this one is a rope and we're pulling on it, we could just be grabbing the box here, but if this is a rope and we're pulling on it, this rope and this rope have different forces. Okay, so the tension in this rope and the tension in this rope are not the same. You could say, though, the tension in a single rope is the same everywhere. So the tension that A experiences from this rope is the same as the tension that B experiences from this rope. Tension in a single strand is the same everywhere. All right, so first thing, we're going to draw a free body diagram. Typically, I would say draw some kind of a diagram. In this case, the diagram's already given. So we're going to use that same diagram, draw a free body diagram. You're welcome to go to the side and draw a free body diagram if it's cleaner, but I'll just do it right on here. So we've got this, let's kind of say here, I'll make this giant dot so we can get this arrow look like it's coming out from the dot. So just remember, free body diagrams, your arrows come outwards from some central dot. So we've got this applied force, we've got gravity, force of gravity on A. We could figure this out, right? It's just mass times 9.8, so 6 times 9.8. We've got a normal force. This is a nice level surface. This block experiences the normal force straight opposite to gravity. There's no other vertical forces. There's no acceleration vertically as well. At least I would assume in this scenario. It looks like there's not going to be any vertical acceleration. This force right here and this force right here are going to be equal and canceling. For block B, similar kinds of stuff. We've got FGB and FN. Let's call it FNB. We'll call this FNA just to distinguish them. This force is canceling this force. Okay, so we'll go single ticks here, double ticks over here to say that this force cancels this force cancels this force. Typically in a question like this, I would need to find force of gravity so that I know the normal force, so that I can calculate friction, because remember, friction is mu Fn. In this case, though, they give me friction. So block A has a magnitude of this friction, and block B has a friction of this magnitude. So let's put the frictions on. So friction A, and from here we've got friction B. Friction B was 12 newtons. Friction A, 8 newtons. Hopefully you can read that, it's here if not. Then we're going to look for the acceleration, but we're also going to look for the tension in the rope connecting them. Okay, so just so you can see this, we won't need this yet until part B, but there is a tension. So you could say, when we do this free body diagram, let's cover up B for 1 sec. When I look at A by itself, I would say for sure the floor puts a force on block A, gravity puts a force on block A, this applied force is there, friction is the floor putting a force. There's also this rope. Okay, so right here, let's see if I can make it so you can see that. There is a force of tension acting on block A. So anything that touches block A puts a force on it. Okay, so gravity, the floor touches it for this force. The floor also makes friction, and then this rope right here also puts a tension force right here. Try to darken this up a little. There's another tension right there. Sometimes we'll call this the force that B puts on A and the force that A puts on B. That's fine. Or you can just call them tension. Sometimes people just use T for tension, and that's also fine. Okay, so that's a little bit hard to see, but something that we do know is by Newton's third law, if this is the force that A puts on B, then this is the force that B puts on A. By Newton's third law, those forces must be equal. Okay, so those two forces are equal and opposite. You can see 1 point's left, 1 point's right. When I do this, if I'm looking for the acceleration of the two boxes, there's multiple ways you can do this, but the way that I would typically do it is I would say, okay, let's look at the system. Okay, so what that means is not just A by itself or B by itself. Don't kind of cover one of them up and just look at one box. I'm going to look at this entire system. Any forces that cancel or balance, I'm not going to include in here. So when I say sum of forces, some people like F net better, that's fine, same thing. When I say sum of forces, what I mean by that is the sum of all of the unbalanced forces in this entire system. Okay, so we've got FA, I should say this, let's make east positive and we'll say up is positive. We'll kind of go standard directions. So something that I've got here is the applied force. That force right there, not balanced. Friction, that's in the negative direction, so I'll put it in as a negative, not balanced. That friction, also not balanced. Okay, this normal force, that gravity, we've already discussed it, they're balanced. Normal force, gravity, balanced. If I look at this as an entire system, then this tension right here, I don't know if you can see that, 3 lines, and this tension right here, 3 lines, those tensions balance. I don't need to include them here. The mass that goes in here is whatever I'm looking at. Okay, so if I'm looking at the system, that's what goes in here, the total system mass times acceleration. Okay, now this is pretty easy. Once you've got to this, it's almost like this is the physics. We've done the hard part of the question. If you can get this line, then for the most part, the rest of this is just kind of subbing in numbers and solving. So if this is 36, this friction here is 8, this friction here is 12. The total mass is 6 plus 12. I'll write it like that, 6 plus 12. You can just say 18. But just as a reminder, it's this mass plus this mass times acceleration. Okay, so what we end up with here, let's see, 36, 24, that would be 16 equals 18a. We divide that, and that is 0.88. That's repeating meters per second squared. For sig digs, we're doing 2 sig digs, so 0.89 meters per second squared. Our forwards direction here is east. We'll stick a vector sign on there. There's kind of good communication. You can show me an unrounded value, show me a rounded value for sig digs. That's all part A. In part B, they're asking for the tension in the rope. So something that we just kind of figured out in doing this is my reasoning for looking at the system when I go through and solve this is so that those tensions will cancel. Okay, those guys cancel as well, those guys cancel, but if I look at this as a system, then those 2 tensions are both there and they both cancel, or they cancel each other. If I'm looking for that tension, then I can't look at the system to find it. I've got to choose one of the blocks. It doesn't matter which one. You could choose A, you could choose B. I like B in this case because it's got less forces. There's kind of, I don't know, there's one less force. This one has the added tension and friction and applied force. So there's one more force here. It doesn't matter though, you can choose either one. In doing that, we're gonna use F equals ma. And when I do this, if I'm looking at block B, I'm gonna say cover up block A, forget everything to do with block A. Let's just look at the forces on block B. Now we've got to ask ourselves the question again, what forces cancel, or what are the balanced forces? So normal and gravity still balance. But again, if I cover up block A, there's nothing to cancel that tension force right there. Okay, so that tension is now an unbalanced force. I'm gonna say F tension is pulling in my positive direction, and friction is resisting in the negative direction. The mass that goes in here is whatever object we're looking at, so just mass B times acceleration. If the acceleration for the system is this 0.89, then the acceleration of block B, it's part of the system, so it's going to have the same acceleration. Okay, so again, let's say minus here. Again, this is really the hard part. If you can get this line, then the rest of it is just subbing in values. Okay, so friction B, that was 12. Mass B, what did we say that was? 12. Acceleration is what we just found. Again, use your unrounded value, that's 0.88. This thing is going to come over here, so we're just going to say F tension is 22 points, and that the 6's are repeating this time. So F tension, the tension in the rope is 23 newtons. Now the tension that we found is east, but you could argue that this tension is also west. Typically for tension, if we're going to write it as tension, we're just going to say the magnitude. Tension is 23 newtons. If, however, you wanted to write it this way, the one that we actually found was the force that A puts on B, then you could say that is 23 newtons to the east, or FB on A, by Newton's third law, 23 newtons to the west. Okay, so if you wanted to write A on B, you could throw the direction in there, then it kind of makes sense. If you're just saying tension, both of those tensions are the same thing. They both point in their opposite directions. People generally just do magnitude. So either one of those is fine, depending on how the question asks. If they ask for what's the force that A puts on B, then put this and include a direction. Hopefully you can see all that. There we go.